Good evening. We are going to start on power electronics and EV drives, lecture number 16. Until now, we had looked at various power converters. The power converters that we had looked at were AC to DC converters. We had also looked at um, AC to AC converters like AC voltage controller, but we looked at it very briefly. After that, we had looked at DC to DC converters, under which we had looked at both isolated and non-isolated converter topologies. Then finally, we concluded the topic of power converters with DC to AC inverters. So these are different classification of converters which we had taken a look at. Now we are going to start on EV drives. So in EV drives category, normally we will be looking at DC motor drive, but we had already discussed DC motor drive in quite a bit of detail when we were discussing about choppers or DC to DC converters. So I will not be venturing into DC motor drives once again. Rather than that, we are planning to look at conventional motors like induction motors and synchronous motors, and how we can control the speed of these motor drives with the help of inverters. This we will be looking at. But before we venture into conventional motors, I am planning to take up special motors, special electromechanical devices like stepper motor, SRM, that is switch reluctance motor, and PMBL DC motor. Out of this, we really do not use stepper motor for electric vehicle propulsion. If at all it is used in electric vehicle, it can be for power windows or wipers. Those can be operated using stepper motor or PMBLDC motor currently. PMBLDC motor is used in two-wheelers mostly because of the limitation of their rating. However, just for the sake of completeness, I am planning to look at stepper motor first. And in stepper motor itself, there are multiple types. I will be discussing variable reluctance stepper motor with single stack and multiple stack. You can ignore multiple stack, that is not very important. But nevertheless, for the sake of completeness, I am discussing variable reluctance stepper motors with single stack and multi-stack, and eventually I will also be looking at permanent magnet stepper motor and then hybrid stepper motor. Okay. Good evening. We are starting on special electromechanical devices or special motors. So, what is the major difference between a conventional motor, electric motor, and a special electromechanical device? The major difference is that conventional electrical motors like DC motor or induction motor or synchronous motor, they can all run without a power electronic converter. Whereas the special electromechanical devices, what we are going to discuss today, cannot exist, cannot run without a power electronic converter. So the power electronic converter becomes an integral part of this special electromechanical device. We are going to mainly talk about three different kinds of special motors. One is stepper motor. Stepper motor is only used for mostly discrete motion. So if I want to probably move a particular valve, probably by 10 degrees, 5 degrees, or let us say I want to move a lens in a gyroscope or telescope by certain angle, maybe in a lathe, if I want to move, let us say, a tool by certain angle. in those taper turning or for thread cutting and such things, in those cases, stepper motors are used commonly. So I would say the major application will be in CNC machine tool applications. And another thing I would say is in gyroscopes, telescopes, and so on, where the lens can be adjusted. And in closing a valve, so valve operation, whether the valve has to be closed or opened, in those cases, stepper motor may be used. And generally, I should say stepper motors are used only for discrete motion, not for continuous motion. So this is one motor which we would be discussing. The second motor that we would be discussing as an extension of stepper motor is switched reluctance motor. So switch reluctance motor is again, as I told you, an extension of the stepper motor. So we would be talking about this, and switch reluctance motor is mainly used for continuous motion, just like how we use DC motor or AC motor for continuous motion. That is also used for continuous motion. So this is switch reluctance motor. And incidentally, switch reluctance motors have been extensively researched for electric vehicle applications. So even for EV applications, this has been extensively researched. But only problem that is found with the switch reluctance motor is that there are huge amount of torque pulsations. So, even with shock absorber and other things, it could be not very comfortable for the people who are riding the vehicle. That is one thing. And second thing is, although the torque to inertia or weight to inertia, power to weight ratio, it is high. This is quite high for a switch reluctance motor, but still the efficiency is not very high. The efficiency is not as high as PMSM. And if you look at PMSM that is being used for electric vehicle application, even every percentage efficiency improvement results in reduction of the battery size, which is one of the costliest elements within the electric vehicle. So we have to be very careful about reducing the size of the battery, reducing the cost of the entire battery pack. Or if you talk about again employing a PMSM for a given size of the battery pack, the range can be extensively improved even if the efficiency is increased by 1%. So PMSM happens to be the winner as far as the efficiency is concerned. That is one reason why switch reluctance motor or SRMs have not really succeeded so much in terms of their being employed in electric vehicle. So we will talk about this switch reluctance motor because in future it is very much possible because of the permanent magnets cost increasing tremendously, or the control technique of switch reluctance motor might improve to such an extent that the torque pulsations may be minimized in future, though they could be a candidate for electric vehicle. The third motor that we are going to talk about is PMBL-DC motor. So this is permanent magnet brushless DC motor. This is very, very similar to PMSM. Only thing is in PMSM, the flux is sinusoidal. So PMSM, the machine generally is a sinusoidal flux machine, whereas PMBLDC motor, if you look at it, that is going to be a trapezoidal flux machine. So we will talk about trapezoidal flux machine particularly because we have already spoken about the sinusoidal flux machine when we were discussing synchronous motors until the last lecture. And this particular PMBLDC machine is available maybe until 30 to 50 kilowatt rating. So generally, they are not very, convenient to be employed in four-wheeler application, but extensively PMBLDC motors are used in two-wheeler application. So most of the two-wheeler application, if you look at it, PMBLDC motor is the one which is used in all the electric two-wheelers. Okay, so if you actually look at stepper motor is in no way directly connected to electric vehicle, but of course, wherever there's a production unit, most of the CNC machine tool applications are employed in all the production units. So in that sense, stepper motor becomes important. As I told you, SRM is an extension of stepper motor, variable reluctance stepper motor. So we would definitely talk about SRM as well, which probably could be a futuristic motor for electric vehicle application. So let us start with now stepper motor. So the stepper motor basically is going to have mainly three types. One is variable reluctance stepper motor. And in this itself, it could be single stack variable reluctance stepper motor or multi-stack variable reluctance stepper motor. And the second type, what we will be looking at is permanent magnet stepper motor. And the third one is a hybrid of these two. So it will incorporate both the features of variable reluctance stepper motor as well as PM stepper motor. We call that as hybrid stepper motor. So we'll be looking at all these three types. But I will dwell more on single stack variable reluctance stepper motor because that is what is actually paving the way for SRM or switch reluctance motor. So the variable reluctance stepper motor, VR stepper motor, the basic principle is somewhat as follows. So in VR stepper motor, especially in single stack case, what we are going to have is a stator somewhat like this. So let us say this is the stator, and let us say the stator has 6 poles and rotor has 4 poles. Always in variable reluctance stepper motor, especially single stack, stator pole and rotor pole will not be equal to each other. The stator pole numbers and rotor pole numbers will not be equal to each other. They will not be equal to each other. So let me say that I'm going to have maybe 2 poles along this, 2 more poles along this, and 2 more poles along this. So I'm going to draw it like this. So let us say I have 1 pole here, and I have to show 1 more pole here. Then let's say there is 1 more pole here, then 1 more pole here, and 1 more pole here, and 1 pole here. So all of them will be of same size, although I have not shown it that way, but this is how it is going to be. So let me call these 2 poles as A and A dash. And let me call these 2 poles as B and B dash. And let me call these 2 poles as C and C dash. So these are the 6 poles that are there in the stator of the variable reluctance stepper motor. Please note that all these portions are made up of iron so that magnetic field lines pass quite easily through this. So this is going to be all made up of iron. So it can be basically laminated and so on and so forth. This is how it is going to be. Now, as far as the rotor is concerned, let us say it is a 4-pole rotor. So I'm just going to show it somewhat like this. I have 2 poles like this and another 2 pole like this. So it is going to have essentially this as the structure. So here is the shaft. So let me call this as 1 and 1 dash. And let me call these 2 poles as 2 and 2 dash. So I am having essentially a 4-pole configuration. You can see these 2 poles here, 2 and 2 dash here protruding like this, and 1 and 1 dash protruding like this. This is how it is. Now, if let us say I have a winding around this, around A, and it continues around A dash as well, and they are connected in series. Similarly, I will have a winding around B and B dash, and I have a winding around C and C dash. And what I'm going to see is I will have a converter somewhat like this. I'm going to have, let us say, this is the DC supply which excites the stepper motor. So I may have simply one device sitting here, which I call as S1. And that is going to energize, let us say, A and A dash like this. And I'm completing the circuit here. And whenever I switch on S1, I'm going to have a current flowing through this A and A dash. And when I switch off S1, if the current is still remaining, it has to find the path. So I might have a freewheeling diode connected somewhat like this. Let me call this as DA. So this can be SA. And similarly, I will have one more switch which is corresponding to SB, and this is going to energize whenever it is turned on, it is going to energize B and B dash. And again, I have to have a freewheeling diode which is DB, which will be connected here for providing an alternating path for the current, alternate path for the current. And similarly, this is going to have SC, which is also going to energize C and C dash from the same DC supply. The DC supply is common to all 3 phases. So this is a very, very simple converter, which is actually allowing either the winding to be energized or the winding flux to be, or it has to be defluxed using the diode DA, DB and DC respectively. So let us say initially I energize. So we energize A and A dash are energized by turning on SA. So we are going to turn on SA and energize A and A dash. Immediately what is going to happen is 1 and 1 dash that will move probably in anti-clockwise direction like this, because of which 1 and 1 dash align with A and A dash, because it is going to become A and A dash will be becoming electromagnets. So it will be attracting 1 and 1 dash. So A dash become electromagnet, because of which they are going to attract 1 and 1 dash. So it is going to move slightly in anti-clockwise direction. Now, the next thing that we are going to do is remove or turn off S1, SA. So turn off SA. So 1 and 1 dash, rather A and A dash are de-energized. A and A dash are de-energized. So the magnetization goes away. Now at this point, we are going to turn on B and B dash. So B and B dash are energized. When B and B dash are energized, Because 1 and 1 dash are already coinciding with A and A dash, there are two options. Either I can imagine 1 and 1 dash move by 60 degrees, because please remember there are 6 poles, so the pole pitch will be 60 degrees. 360 divided by 6. So that will be 60 degrees. Whereas if I look at the rotor, that is going to have a pole pitch of 190 degrees. So there are two options. Either 2 and 2 dash can move in counterclockwise by 30 degrees, or 1 and 1 dash move by 60 degrees in clockwise direction. So there are two options when you energize B and B dash after A and A dash. This will move by 30 degrees in counterclockwise. So obviously, less amount of work needs to be done when you talk about the second option rather than the first option. So the first option will not be adopted. The second option will be automatically taken over, because nature generally looks for the minimum work condition. So you are going to see that 2 and 2 dash align with B and B dash. Now the next thing that you are going to do is to again turn off B and B dash, and then instead turn on C and C dash. So when you turn on C and C dash, again you will have already 2 and 2 dash have aligned with B and B dash. So 1 and 1 dash will be closer. So it will again move by another 30 degrees. So at this point, 1 and 1 dash align themselves with C and C dash by moving 30 degrees in counterclockwise direction. So you would see that for every step, every pulse that you are giving, basically the poles of the rotor, they are moving or they are stepping by about 30 degrees. So if I try to calculate the step angle, generally the step angle is going to be 360 degrees divided by number of rotor poles minus 360 degrees divided by number of stator poles. So we already said this is 90 degrees. What we calculated as pole pitch for the rotor was 90 degrees. So 90 degrees minus 60 degrees. So the step angle in this particular case happens to be 30 degrees. So what we are getting is 30 degree step angle in this particular case. So for achieving 360-degree motion or one revolution, complete revolution, you will require basically 12 pulses, because 12 multiplied by 30 degrees, that is going to give us 360 degrees or one revolution. But all the same, A and B and C, this is the sequence we are adopting repeatedly. So ABC sequence gives us counterclockwise rotation. ABC sequence is going to give us counterclockwise rotation, and whether the current flows in the up to down or down to up, it doesn't matter at all. whatever the current direction, if it is flowing in this direction or the opposite direction, that does not matter, because you are only having a piece of iron here, and this piece of iron will be able to move no matter what, whether A becomes North Pole and A dash becomes South Pole or vice versa. So the direction of current is not going to make any difference in terms of the direction of rotation. So direction of current does not determine, it does not determine the direction of movement. Whereas if instead of ABC, if I just say C, B, A, and then again C, B, A. So if I try to do this as the sequence of rotation, you can analyze this, it will go into clockwise direction. So the sequence of firing the devices, that actually determines in which direction your motor is rotating, whether it is clockwise or counterclockwise, that is determined by this. Second thing I would like to say is, although we say 30° is the step angle, if rather than that, I fire A, then I pass half the current through A and half the current through B. So I fire both A and B if I'm able to control the current in a fine manner. So I do first only firing of A, then firing of A and B with half the current in each of the windings. Then I fire B, then I fire B plus C, then I fire C, then I fire C plus A, and so on. If this is repeated, then instead of having 30°, we would be able to get actually the step angle of 15 degrees if I try to do that. So I would be able to adjust the step angle to a very minute value if I am able to fire two of them simultaneously, or if I try to have 3:1 current ratio, then I make 1:1 current ratio, then 1:3 current ratio, and so on. I would be able to adjust the step angle in a fine manner. So to adjust the step angle, to adjust the step angle in a fine manner, either I have to have more number of rotor and stator poles, which we can definitely carve out more number of rotor and stator poles, because after all, these are only iron pieces. It's not anything very expensive. It is only a piece of iron. So we should be able to do that. Or we should be able to fire like what we said earlier, then A and B together, then B and C together, and so on with appropriate current values. So we can do this to reduce the step angle or have the step angle in a fine manner, varying in a fine manner. That will be possible. One point that we need to mention about variable reluctance stepper motor is you won't have any control over at what point the rotor stops if the power supply is suddenly going away. So if there is a power cut, you will not have any torque to detain the rotor in a particular position. So there is no detent torque. On the other hand, if I'm going to have at least either rotor has a magnet or stator has a magnet, because all the portions are made up of iron, it will be automatically attracted to the closest pole if there had been a permanent magnet. There is no permanent magnet here. There is no retention of magnetism here. That is the reason why detent torque. Detent torque is if power supply is cut off abruptly, is there a torque? That particular torque is known as detent torque. If there is some residual magnetism or if there is a permanent magnet, then that is going to cause some torque to be retained or to detain the rotor in a particular position. That is known as detent torque. So this can sometimes give rise to some problem, especially in machine tool applications. You don't want something to go wrong in terms of thread cutting or taper turning or any of them. You want to make sure, even in a pick and place robo, you want to make sure that it comes to a halt in a predetermined position. If that is not there, detent torque is not there, you cannot ensure that the robotic arm or anything else comes to a halt in a predetermined position. One more thing I would like to say is the stepper motor, especially variable reluctance stepper motor, will be of very limited rating. See, one major advantage of stepper motor is that we know for every pulse, this particular 6 by 4, that is stator poles are 6 and rotor poles are 4, 6 by 4 variable reluctance stepper motor will always will move by only 30 degrees. So I don't even need a feedback or sensor for sensing the movement of the motor, because I know if I have given 5 pulses, then it would have moved only by 5 multiplied by 30 degrees, which is corresponding to 150 degrees. So if I know for sure I have given only 5 pulses, I know it has moved by 150 degrees. So I don't need really any sensor or feedback control system. It can be simply a open loop control configuration, because I know clearly how much my rotor has moved. It's not a problem. But sometimes if there is overloading of the motor or rotor, if you are going to have overloading of the rotor, this can miss some pulses. The rotor can miss some pulses, which means you may not be very sure that it has really moved by 150 degrees even after 5 pulses if you have overloaded the rotor. So from that viewpoint, you have to be very, very mindful of how much you are loading the motor for. So there are two ranges that we normally talk about. If I try to look at what is the kind of torque to which I am subjecting this particular motor, I will be able to probably handle, let us say, until certain torque. Let us say this is TE1. So I'll be able to handle this for, when I'm starting from the rest position. Your rotor is already not having any kinetic energy stored. It is very slowly picking up the speed, so it will be able to handle probably certain amount of torque. But if it is already up and running, it may be able to handle a little bit more torque, and it will be able to handle, because of the inertia of the rotor, it will continue to rotate even if you are not energizing any phase. So we call this as slew range, which is corresponding to the rotor already up and running. So this is generally known as start range, where you have to take into account the inertia of the rotor also in terms of storing the kinetic energy. So this actually tells you that for lower pulse rates, you will have, actually, if you are talking about a larger torque that is to be handled by the rotor, it will be able to go only with the lower pulse rate. So if I say this is N1, whereas this is N2, already if the motor is up and running, it will be able to handle a higher pulse rate, whereas if it is just starting from rest, it will be able to handle only a lower pulse rate with a lower amount of torque. So we should be mindful of this in terms of what is the maximum torque value my motor can be subjected to, and what is the kind of maximum speed it can achieve with the particular torque already on the rotor shaft. So this is a very, very important kind of parameter that is specified in the stepper motor's data sheet normally. How much will it be able to handle as the torque during starting, and how much will it be able to handle the torque with already up and running rotor, and what is the maximum speed up to which it will not miss any of the pulses in terms of movement. So in general, variable reluctance stepper motor, especially with single stack, is used only for low power applications. And where I want to have really very, very precise movement, very small steps and precise movement. It can be done very well by a variable reluctance single stack stepper motor. Whereas if I try to look at a multi-stack configuration, a multi-stack stepper motor configuration, this is a multi-stack stepper motor. So in this configuration, what you are going to see normally is the stator poles and rotor poles are equal in number. Both of them are going to be equal in number, and there can be more than one stack. So we are going to have, in this particular case, 3 stacks are shown. So the stator has 3 stacks, and they will not be staggered from each other. The stator poles are not staggered, rather they are actually in line with each other. Whereas the rotor poles are going to be staggered from each other. So let us say if there are n poles, stator poles or rotor poles, and m stacks. The rotor poles are staggered from each other by 360 degrees divided by n, product of n and m. So if I say that there are going to be, for example, 12 poles in the stator, and if let us say there are 3 stacks, so this is going to be 360 degree divided by 12 multiplied by 3, that is 36. So that is going to be 10 degrees. They are going to be staggered from each other by 10 degrees. Now what happens is, let us say these are the stator poles. I'm just showing the stator pole somewhat like this. They will be uniform, although I'm showing it somewhat non-uniformly. So these are the stator poles. Now, as far as the rotor pole is concerned, let us say one set of rotor pole is somewhat like this. So this is going to be stack 1. So this is stack 1 of the rotor. Okay. Now the stack 2 will be staggered from stack 1 by 10 degrees. So I'm going to have stack 2 somewhat like this. So this is going to be stack 2 of the rotor pole. All of them are now, all the stacks are connected to the same shaft. So this is going to be stack 2. And as far as the stack 3 is concerned, I'm going to have the stack 3 somewhat like this. So this is going to be stack 3. So I have the same 12 poles which is sitting in the stator as well as rotor, but they are going to be staggered from each other by 10 degrees. So this is going to be about 10 degrees. And this will also be between these two also, it will be about 10 degrees. So we are going to have, let us say this as stator stack. All of them are going to be coinciding with each other. And this is going to be stack A of rotor. And this is going to be stack B. And this is going to be stack C. So when initially I fire or I energize only stack A of the stator, when I energize stack A of the stator, you are going to see that rotor stack A aligns itself with this particular stack A. After that, I'm going to de-energize stack A, then energize stack B. So this will move in this direction by 10 degrees, so that it aligns itself with stack B, which is energized. Then stack B will be de-energized and stack C will be energized. So this will also move by another 10 degrees. So basically you are going to have the step angle to be same as whatever is the staggering angle between rotor stacks A, B and C respectively. Then after that again when you energize stator stack A, then again there will be a 10-degree movement so that this particular second teeth aligns with this one. So you will have very fine movement taking place in multi-stack variable reluctance stepper motor, but you have to have basically stack A energized first, then stack B energized first, and stack C energized next. And after that, again stack A and so on. So this will allow basically very, very fine movement in variable reluctance stepper motor as well. Now, as far as permanent magnet, because we said that we have three types of stepper motor. The first one we said was variable reluctance stepper motor. We have looked at that in both single stack and multi-stack configuration. Now we are going to go into quickly the permanent magnet stepper motor. So as far as the permanent magnet stepper motor is concerned, we are going to have, let us say, a 4-pole configuration in our stator. So let us say I'm showing some 4-pole like this. So let us say I call this as A and A dash, and I call this as B and B dash. And I'm going to have A and A dash maybe having a winding in this particular configuration. So when I energize A and A dash, let us say this makes North Pole and this makes South Pole here, maybe. And I'm going to have a magnet, permanent magnet sitting like this, and the shaft is somewhere here. So let us say the permanent magnet is in such a way that this is South Pole and this is going to be North Pole. So obviously A will attract South Pole and A dash will attract North Pole, and the rotor will align itself like this. After that, if I energize B and B dash windings such that I'm going to have again North Pole here and South Pole here, obviously this will move this way and this magnet will move this way. So there will be clockwise rotation. So the rotor has permanent magnet poles, whereas stator has energizing windings. So here, depending upon the direction of current, this will become North Pole and this will become South Pole. Or if I change the direction of current, this can become North Pole and this can become South Pole, due to which the rotor will start rotating now in counterclockwise direction. So, because of the presence of permanent magnet in the rotor, the direction of current in stator windings will determine the direction of movement. So it is unlike variable reluctance stepper motor. Here the direction of current is going to play a vital role. That is one thing. The second thing is, because of the presence of permanent magnet, there will be detent torque. So when you switch off the excitation to all the phases, whatever is the closest to pole of the stator, there the rotor will come and rest so that it gets aligned completely. So there will be detent torque. So you don't have to be skeptical about what is the exact position at which the rotor has rested. It can only rest aligning with B and B dash, or it can rest aligning with A and A dash, whichever is the closest. That's not a problem. So you cannot say what is the rest position. You cannot be really doubting about what is the rest position. The third thing we have to say is, because the permanent magnet presence in the rotor, it is not generally possible to carve too many poles, because you will be wasting a lot of permanent magnet material otherwise. So you cannot really carve too many poles in the rotor. So the step angle is somewhat large in permanent magnet stepper motor. But of course, the torque produced will be somewhat higher in a permanent magnet stepper motor because of the presence of at least some magnet on the rotor side. Stator is devoid of magnet. It has only the winding, but the rotor has magnet, because of which you would be able to generate a little larger torque. That is possible. In hybrid stepper motor, on the other hand, which is a mixture of the variable reluctance stepper motor and permanent magnet stepper motor, you will have the stator again the same way. So the stator might have a large number of poles carved. Okay, so we may have large number of poles carved like this in the stator. I'm not showing again uniformly. But as far as rotor is concerned, let us say I design it for a 4-pole configuration or something like this. This is going to be the 4-pole configuration. I may still have maybe North Pole buried here. There is one North Pole buried here. There is one more North Pole buried here. Whereas I may have a South Pole buried here and a South Pole buried here. And I should be able to have, small magnets buried inside, and I can have a larger number of teeth carved all over. So this actually allows us to have more number of teeth carved along the core. Along the core, I can have more number of teeth carved in the rotor, but small magnets can be buried inside. So in that sense, this will have detent torque and we may be able to make small step angles will be possible in this particular case. So that is one of the greater advantages of hybrid stepper motor. You essentially, eliminate the disadvantages of variable reluctance stepper motor as well as the permanent magnet stepper motor. So you are able to have small step angles possible, and you will be able to have detent torque also. That is not a problem. Okay. So we will now go over to switched reluctance motor. So in a switched reluctance motor, what we are looking at is very, very similar to, as I told you, variable reluctance single stack stepper motor. So you are not going to have any difference between the structure of single stack variable reluctance stepper motor and switch reluctance motor. So let us say this is going to be our stator of a 6x4 SRM. So 6 is the stator pole number and 4 is the rotor pole number. Okay. So let us say I'm going to have 1, this is 2, and I'm going to have 3, and I'm going to have 4, and I'm going to have 5, and I have 6. So these are the 6 poles for the 6 stator poles of the variable reluctance stepper motor. And that is also now functioning as our SRM. So let us say this is A, and this is going to be A dash, and this is going to be B, this is going to be B dash, and this is going to be C, and this is C dash. Okay, so this is our complete stator structure. Now, as far as the rotor is concerned, as I told you, I'm going to have probably 2 poles here and 2 more poles here, and I'm showing 6x4 structure for this. So this is the rotor. So let me call this as 1, and this is 1 dash, and this is going to be 2, and this is going to be 2 dash. Okay. So the energization again can be done exactly like what we did in the case of stepper motor. So we said that this is the kind of energization circuit, converter circuit we have for the stepper motor. A similar thing can be employed here as well. So when we look at the inductance profile, how A-phase inductance is looking, whenever I'm going to have either 1 coming closer, the inductance will be very, very high, or 2 coming closer, the inductance of the winding that is wound around A-phase, that will be high. Or when 1 dash comes or 2 dash comes, it will be very high. So if I try to look at the inductance profile, I am essentially going to have, let us say this is totally 360 degrees. And let us say this is 180 and this is going to be 90. So let us say this is 90, this is 180, this is 270, and this is 360. So we are talking about rotor position theta. So let us say this is actually theta equal to 0 degrees, and it is rotating in this direction like this. So at this point, your inductance is probably maximum. So from maximum inductance, it will almost come down to 0 like this, and then it will remain in minimum for some time like this. And then it is, sorry, I have to draw it like this. For the entire 90 degrees, it is actually going to cover like this. It is going to come down like this, and then it will remain minimum, and it should have reached the maximum exactly at this 90-degree point. So this is going to be somewhat like this. It will come down and it will reach down, and it should have reached the maximum exactly at 90-degree point. And again, it will go like this. It will come down and it will reach the minimum, and then it will go to the maximum point at 180 degrees. So this will repeat itself somewhat like this. So it is going to repeat itself somewhat like this. So this will be the kind of inductance profile you will be seeing. So because there are 4 poles, if I say this is inductance of A pole, A and A dash, if I try to look at this as inductance of A and A dash winding, now for B and B dash, it is exactly shifted by 60 degrees. So I should show it as though, let us say this is probably 60 degrees. No, I have to divide this into 30-degree intervals. So this is 30, this is 60. So exactly at 60 degrees, I'm going to have again for B phase, it will be somewhat like this. So this is going to be like this, and it will come down and it will go up like this, and then it has to go up like this. This is how it will be staggered. So LB will be staggered from LA. Exactly, it will have the same wave shape, but it will be staggered by 60 degrees. So I should say this should again come down like this, and it will go up like this. So this is how it will be. And LC, so LA has 4 peaks within 360 degrees because there are 4 rotor poles. And LB will be shifted by 60 degrees from LA because stator pole pitch is equal to 360 degrees divided by 6, which is equal to 60 degrees. Okay? And similarly, I should be able to say LC will be, LC is the inductance of C pole winding, stator pole C winding. So LC will be shifted again by 60 degrees from LB. So this is the way we are going to have this inductance structure. Now, every time A phase is energized, one of these poles, either 1 dash or 2 and 2 dash, they are going to align with A phase. So whenever they are aligning, inductance will be maximum. So every time the machine, the rotor poles are in non-aligned condition, they will try to align themselves. That means the inductance, whenever it is slowly increasing, that is where it is going to have any incentive to develop torque. So whenever the inductance is increasing, you are going to see a development of torque. Whenever the inductance is decreasing, there will be a negative torque developed. So the positive torque will be developed only when the inductance is going towards increasing condition. So if I try to look at A phase, there are 4 conditions under which I will be able to energize the A phase winding such that positive torque will be developed. So I have to know exactly where the rotor position is before I energize either A phase winding or B phase winding or C phase winding. So I need to know necessarily how the rotor position is before I energize either A phase winding or B phase winding or C phase winding. So switch reluctance motor necessarily need to have a rotor position sensor. So rotor position information is a must for suitably firing the stator phase windings, whether it is A phase or B phase or C phase windings, so that positive or motoring torque is developed. Because if I try to fire the stator winding, A phase winding, for example, only during this position, I'm going to get positive torque. Rather, if I try to fire it during this position, I'll get only negative torque, which is detrimental to the motoring operation. So that is the reason why the control of switch reluctance motor is not easy. I definitely need rotor position information for controlling the switch reluctance motor properly.